Hello everyone. So we have already discussed the basics or introduction of shock waves. So in this lecture, so we will talk about more on shock waves. Shock waves are like produced when the amplitude of stress wave greatly exceeds the when amplitude of stress waves greatly exceeds the dynamic yield strength of the material. So, dynamic yield strength or flow strength is that yield strength at that strain rate, that is which is different than the quasi-static or at slow strain rate. If it is the amplitude is greatly exceeds greater than the dynamic yield stress, so we can neglect the shear stress as compared to hydrostatic component of stress. So that means a high pressure state high pressure state will propagate through the material. So or into the material. The equation of state for an ideal gas for isentropic process that means isentropic process means change in entropy is equal to 0, or isentropic means adiabatic and reversible. So we are neglecting the shear stress as compared to the hydrostatic stress. So we will now see the treatment for an ideal gas, that is equation of state, which is like your Boyle's law, Charles' law, and like classical ideal gas laws, like we got PV is equal to nRT. So similarly, these are equation of state. That means it's in thermodynamics, thermodynamic equation, the relating the state variables which describe the state of a matter. So that means in equation of state is actually we can in general form we can write it this way, but for this isentropic equation of state for an ideal gas or isentropic process, so this will be we write it as PV to the power gamma is equal to constant K, let us say K constant. So this is what we can do is we can differentiate differentiating we can get as gamma PV gamma to the power minus 1 dV plus V to the power gamma dP equal to 0, which will give us dP dV is equal to minus gamma PV. So it means we can write when pressure will increase, dP dV modulus of dP dV will increase, and that means the compressibility of the gas, will decrease. The compressibility generally we have V 1 by V dV dP. So this compressibility of gas will decrease. So earlier we found that the disturbance velocity d sigma d epsilon by rho to the power this. So disturbance, that we can call the velocity of disturbance. So now for a gas, if we assume like one dimensional conditions, the velocity of disturbance the disturbance means let us say stress wave in this case. So or it's you can call it is let us say the pressure discontinuity, as it is related to high pressure. So pressure discontinuity. So this disturbance velocity will be equivalent to dP dV by rho. So this is for a gas in one dimensional case. So now that says that we high amplitude isentropic disturbances travels faster. That means high amplitude means you have a high pressure, and that as you can see from here, if pressure increases dP by dV increases, so velocity will be higher, or it will travel faster. So this is, I will write it here, P dP by dV in your velocity of disturbance, as I will just write Vd will be higher. So what will happen, the high amplitude part will have a steep front. So a steep front will be developed because the high amplitude disturbances will travel faster than the low amplitude disturbance. So the shock wave is also defined as a discontinuity of pressure, temperature and density rho. So it is also defined this way. So this concept of shock waves and then its treatments, especially what we learn a little later about Rankine-Huguenot treatment, that means Rankine-Huguenot conservation equations for shock waves. So that these equations can be easily understood if we look at the another treatment of which is analogous to this, Davis 1987, which is analogous to that, not exactly what we will be doing is not exactly the shock wave treatment, but it is something analogous to it, or it's a the concept is same. So what it shows is a cylinder. This is a cylinder with a piston inside. So this one is the cylinder and the piston will move towards right. So this is a piston, now it has rest. Let us say this is idealized piston, and this is this part we have this has compressible material, or in this case, as we know, we can assume it as a fluid, compressible material. Then let us say this is at time t equal to 0, and the pressure here is P naught, density here is rho naught, and internal energy per unit mass is let us say E naught, and the velocity of these particles which is u naught, and that can be, if it is stationary, it can be equal to 0. So now at time t equal to t1, let us say, the piston moves forward, and so this velocity of the piston is, we will write as a up. So what will happen is, so we have this compressible fluid. Now when you are compressing with this piston, so some part of the fluid, like this part, will be compressed now. So density will be higher here. So this is the compressed region, and we can write the pressure, the density, and the internal energy per unit mass for this region like this, and the other region, it will remain the same. It will remain the same, P naught, rho naught, and E naught, and then this is called this boundary is called the front of the disturbance. So this boundary is, we will call, I will write it here, disturbance front. Disturbance front. So this disturbance is, let us say we are here, we are not calling it as a shock wave front or something. So here we will just say that this is pressure discontinuity is the disturbance, and this is the disturbance front. So this disturbance front will move forward with a velocity us, and as we know, this velocity of these particles are u naught in this side, and here we have the piston velocity as up. So I will write it here, up is piston velocity, and us is velocity of propagation of the disturbance, we can assume that this this part which is not compressed, that is stationary part of the fluid, and this part is moving part. That stationary part may not be always stationary, but for now we can assume it is stationary, and the part that is compressed is we can call as a moving part, moving the material or fluid, and the boundary between the two is the disturbance front. That is the disturbance front. When the piston will move, it travels a distance up T1, and at the same time the disturbance will move a distance US T, and sorry, it's too messy here, but so what we can do is the other part, that this part I will write it somewhere else. So this part is US minus UP multiplied by T1. So that is the thickness of the compressed region. So sorry, this is US T1, that is because T at time T equal to T1, and the earlier one was when piston is at rest, and that is T equal to 0. So now here what we will do is we will have will apply the conservation of mass, conservation of energy, and conservation of momentum. So earlier also we discussed for elastic wave propagation. So what we did is for elastic wave we had conservation of momentum. So we used conservation of momentum. So here for shock waves we will use conservation of mass, conservation of momentum, and conservation of energy as well. So but this is exactly not the shock wave treatment, but this is analogous to it, that is piston in a cylinder, which was initially proposed by Davis 1987. So first we will go for conservation of mass. Conservation of mass, the initial uncompressed material or fluid, this is uncompressed, this part uncompressed material. So here the mass of this is we can have it as US T1 rho naught. So this is the initial mass uncompressed material, which is after compression actually it will look like rho US minus U naught T1. Okay. So initially the thickness was US T1 uncompressed and US minus U naught T1 is the compressed mass thickness, and we are assuming A equal to that cross sectional area A equal to 1 unity, and so that means density mass into density. So this is our mass into density, sorry, volume. So we have this volume into density. So So this is for uncompressed, the left hand side, and the right hand side is the compressed. So when we cancel out the time t1, so the final expression we can write it as us minus u naught multiplied by rho. So this is the relation we get from conservation of mass. And then momentum, conservation of momentum we will use. Conservation of momentum, which will give us the final momentum, which will be rho us minus up. So mass, and this mass is till this point, and this is the velocity. So this is the final momentum, and the initial momentum is 0. We do not, the piston is at rest, so it is 0, and then is equal to the impulse, that we know that equal to the impulse, which will be the final pressure minus the initial pressure multiplied by T will give us the impulse. So now if we cancel out the T from both, we can write here T1 for both. So us minus up multiplied by up will give us P minus P naught. So this is the equation of conservation of momentum. So we have talked about conservation of mass and conservation of momentum. Now we will see the conservation of energy. We know that the conservation of energy is like work done by external force is equal to change in internal energy plus change in kinetic energy. So change in internal energy in this case, is the E, the mass, the internal energy per unit mass of the changes in the final internal energy, which will give it as rho us minus upt, which is the mass of that, and then rho naught us t. So this is we'll see from this figure. So us t1 is the thickness of the compressed, so uncompressed region earlier, and then the thickness of the compressed region is us minus upt1. So that's the mass. If we talk about mass, then and we are assuming area equal to unity here. Everywhere we are assuming area equal to unity. So this is for the mass of the uncompressed region. So and this will give us actually E minus E naught equal to rho naught us T1. So this is T1 actually. This part from the conservation of mass, we got that us rho naught is equal to us minus u naught multiplied by rho. So that will give us us rho naught. So now final expression will be this, and change in kinetic energy kinetic energy will be the final kinetic energy half rho us u naught us by up t, that is the mass and velocity square minus the initial kinetic energy, that is the piston will be at rest. So, that will give us half rho naught us up square t. Same this from the conservation of mass, this part will be us rho naught. So, this will give us this expression. Now, for a stationary disturbance front is stationary. If actually disturbance is stationary, so then that work term will not influence here. So, we will have only change in internal energy, change in internal energy equal to change in kinetic energy. So, that will give us these two terms if we equate it. So, we will get it as E minus E naught is equal to half of up square. So, this is basically from actually initially proposed by Davis 1987, and which is for a compressible fluid with a in a cylinder and pushed forward by idealized piston, and then we applied the conservation of mass, momentum and energy, and we can see the final expressions from these equations. So, in the next lecture we will be talking about Rankine-Hugenoid treatment of shock waves, which will be very similar, analogous to this treatment. That is why we have gone through this treatment in this lecture. So, the rest of the shock wave discussion we are keeping it for the next lectures. Thank you.